Hello everyone from Math 2200, Discrete Mathematics. It's Professor Wenson here again with a video on your section, your Zybooks section 9.4, titled The Greatest Common Divisor and Euclid's Algorithm. So let's just get into it. Alright, so as they say here, you've already seen how to compute the greatest common divisor of two numbers if the prime factorizations for those two numbers are already known. And then it goes on saying, unfortunately, computing the prime factorization for an integer is sometimes a hard problem, especially for much larger integers. And I'll let you read the rest of this. So here is the basis of what's called Euclid's algorithm, and it has to do with the greatest common divisor of two positive integers. This isn't Euclid's algorithm, this is just a theorem, but this is all leading up to Euclid's algorithm. So let x and y be two positive integers. Then the greatest common divisor of x and y is equivalent to the greatest common divisor of y mod x and x. Now remember, y mod x is just the remainder when you divide y by x. So I guess they're going to assume here that y is greater than x. Right? Because if x were greater than y, you're not going to be able to divide y into x. Alright, and this gives us like a little tool to kind of keep reducing things mod x until we eventually see what the greatest common divisor of two numbers is. Alright, now I'll let you read through the proof here. Alright. So suppose that x and y are large numbers and that x is less than y. According to the greatest common divisor theorem that you just saw, y can be replaced with y mod x in the computation of the greatest common divisor of x and y. And the result will be the same. And since y mod x is a smaller number than both x and y, computing the GCD with y mod x instead of y is an easier problem. And then you can repeat this process. Right. And eventually the algorithm is left with two numbers x and y where y mod x is 0, right? So basically where y is a multiple of x. And if that happens, then y is a multiple of x, and the greatest common divisor of x and y is x, the smaller of the two. The animation below illustrates this repetition of the process of replacing the large number with the remainder when you divide by the smaller number. This is Euclid's algorithm until you eventually get down to when the two numbers are multiples, and then the smaller of the two numbers will be the greatest common divisor. So here's an example. I'll actually play this animation here for you. So say we're asked to find the greatest common divisor of 675 and 210. So first let's find, again, the larger number 675, the smaller number 210. What's the remainder when I divide 675 by 210? Alright, now 210, you do multiples of 210, you got 420, 630, and 630 is 45 less than 675, so you have a quotient of 3 and a remainder of 45, and that's the 675 mod 210. Alright, so now according to that greatest common divisor theorem, this greatest common divisor of 675 and 210 will be equivalent to the greatest common divisor of 210 and 45, right? I'm replacing the larger number by this remainder when I divide by the smaller number. And that's what they're going to do next. switch it over and then just repeat the process. So now they're talking about what's the, now they're trying to find, initially it was the greatest common divisor of 675 and 210. By that greatest common divisor theorem, that'll be equivalent to the greatest common divisor of 210 and 45. And if we're doing this, 45, you got 45 times 4 is 180, plus 30 would be 210, so the remainder is 30 when you divide 210 by 45. So then the greatest common divisor of 675 and 210 is the same as the GCD of 210 and 45, which would be the same as the GCD of 45 and 30. And then when trying to find the GCD of 45 and 30, well, when you divide 45 by 30, the remainder is 15. All right, so then the GCD of 45 and 30 is exactly the same as the GCD of 30 and 15. But wait a minute, 30 is a multiple of 15. See, the remainder is 0, right? So the greatest common divisor of 30 and 15 is just the smaller of the two, right? Since one is a multiple of the other. So 15. So then going all the way back to the beginning, then the greatest common divisor of 675 and 210 is 15, right, after all that. Now I know you could have found that with the prime factorizations, right? These numbers aren't that large, right? You could have found the prime factorization of 675, the prime factorization of 210, and you would have seen that the only primes they have in common are 3 and 5, and 3 times 5 is 15, but this is just an alternate method, a repetitive process, right? This algorithm, Euclid's algorithm, to finding the greatest common divisor of two numbers. Just constantly finding remainders until you get down to a pair of numbers where one is a multiple of the other. All right, so let's try that on. I'm going to try that on paper. Oh, well, before we get to on paper, looks like they write out in pseudocode Euclid's algorithm for finding the greatest common divisor. So the output's going to be the greatest common divisor of x and y. If y is less than x, they switch them so that the smaller numbers on the left and larger numbers on the right. And then they assign r to be y mod x. Alright, so then this while loop is run, while the value of r is not 0. Alright, so basically while y is not a multiple of x, we run these steps in the loop. So y is assigned the value of x is assigned the value of r, and r is assigned y mod x. And again, you start over, check this condition. If this is true, if r is still not 0, you keep going. And then at the end, when r is 0, you return the value of x, right? That final value of r, that final non-zero remainder. So looking at this algorithm, which produces the greatest common divisor of two numbers, let's consider Euclid's algorithm with input integers 156 and 54. Alright, so I'm going to do this by hand. First, let's find the greatest common divisor of 156 and 54. The way they did in the animation up here, okay, using Euclid's algorithm. Right. So I'm going to so I want to find the greatest common divisor at the largest number that goes into both of these numbers evenly. All right. So first I want to find how many times is 54, what's the remainder when I divide 156 by 54. So what is 156 mod 54? Well, let's see. 156 would be 54 times, now 3 would be too big. 54 times 2 would be 108. 54 times 3 would be larger than 156, so it'd be 162. So 54 times 2, which is 108, And then 108 plus 48, right, plus 48 would be 156, and this is the remainder I'm looking for here, right? And again, if you're doing mod 54, right, your result should be from 0 to 53. All right, so this is 48. So now this greatest common divisor, by the greatest common divisor theorem that we just saw, the greatest common divisor of 156 and 54 will be equivalent to the greatest common divisor of 54 and 48. It's kind of, again, replacing the larger number with the remainder when you divide by the smaller number. All right, and now I want to find 54 mod 48. All right, well, this one's simple, right? 54 is 48 times 1, plus 6. And there's your remainder. So now back in this, this is going to be equal, by that greatest common divisor theorem, this will be equal to the greatest common divisor of, and then again replace 54 with 6 now, and I'm just going to put it so that the largest numbers first, doesn't really matter, of 48 and 6. And then what's 48 mod 6? That's 0. Right? Because 48 is a multiple of 6. Right? 48 is 6 times 8 plus 0. So I'm going to stop here. All right. If you're down to a pair of numbers where one is a multiple of the other, then that smaller number will be the greatest common divisor. So when we're all done here, we're seeing that the greatest common divisor of 156 and 54 is 6. Right, 6 is the largest number that goes into both 156 and 54 evenly. Now we could double check this by, because these numbers aren't very large. Right, we can double check this using the prime factorizations. So like 156, this is 2 times 78, and 78 is 2, also has a factor of 2 also, so 2 squared times, and then 39, and 39 is 3 times 13, so we have 2 squared times 3 times 13. Right, there's the prime factorization for 156. And then 54, right, 54 is 2 times 27, and 27 is 3 cubed, right, so 2 times 3 cubed. And there's the prime factorization for 54. So the greatest common divisor of these two numbers, remember we'll have some 2's, we have some 3's, we have some 13's, and then the powers on these were the smallest power you saw. The smallest power of 2 is to the first, the smallest power of 3 is also to the first, and then the smallest power of 13 is technically to the 0, because there is no 13 in this factorization of 54. And see, I have 2 times 3 times 1, which is 6. So check on that. That's the same number I got using this Euclidean algorithm, or Euclid's algorithm. All right, but you don't have to do this, right? This is some side work here. That was just so I could verify it for myself. Just double check my work. All right, so going back, they're going to have you run through this basically in that loop, in that while loop. So you see here back in the loop, the value of x is 54, the value of y is 156, right? and so it runs through this now. Y is bigger than x, so this isn't run, this if statement. Then it assigns a value of r, right? R is y mod x, which I already told you, 156 mod 54 is 48. Right, so the value of r would be 48, and r is not 0, so then y becomes 54, x becomes 48, and r becomes 54 mod 48, which was 6. And since r is still not 0, it starts over, and then y becomes 48, x becomes 6, and then r becomes 48 mod 6, which is 0, and then the thing stops, and you return the value of x, which was 6. Alright, you'd only run this thing basically, I think, twice. So what is the value of r at the beginning of the first iteration of the loop, right? Remember, the first value of r is that 156 mod 54, which was 48. And then what is the value of r at the beginning of the second iteration? That was 6, right? Because again, r is 48 here. I already read through it. Y would be given the value 54, x would be given the value 48, and then r would be 54 mod 48. So then when you start the next iteration, the value of r is 6. And what is the value of r after the second iteration? It's 0, because you had the 48 mod 6. So you're done. How many times does the loop execute on input 156 and 54? How many times did it run? I would have had to have run through that loop 3 times, right? Once when r was 48. No, sorry, once when r was 48. Once when r was 6. And then r would have been 0. So I really would have only had to do it twice. So the loop would only run twice. And then what is the greatest common divisor of 156 and 54? It is 6, as I've shown you several times now. All right. So again, hopefully watching me do that on paper too helped. All right, what's going on when you're running Euclid's algorithm to find the greatest common divisor of two numbers. It's really just a lot of finding remainders. All right, what's the remainder when I divide the larger number by the smaller number? And then replace the larger number with that remainder, and then start over. And you keep going down till you get a pair of numbers that, one is a multiple of the other, and that smaller number is going to be the greatest common divisor of your original two numbers. All right. Sounds like a lot, but hopefully when you watch me do it, it was pretty simple. All right. Now, the extended Euclidean algorithm. We're going to run through the way I just did it. All right. Run through the Euclidean algorithm as I did before. But then afterwards, we're going to be expressing the greatest common divisor of our two numbers in the beginning as a linear combination of those two numbers. So suppose x and y are integers. Then there are integers s and t such that the greatest common divisor of x and y is sx plus ty, right? So what we're going to be doing is kind of running backwards. So I'm going to run through the Euclidean algorithm and then kind of go backwards. All right. We're going to do a lot of substitution, as you're going to see. All right. So the greatest common divisor of two numbers should be able to be expressed as a linear combination of those two numbers. All right. So again, I'll show you the you know what? I'll just do this one. You can play this animation here. You got what's the greatest common divisor of 675 and 210. Right? It's 15. All right, and they show you how they went through the same. It's kind of the same steps as earlier. All right. And then now you should be able to write 15. You should be able to express 15 as a linear combination of 675 and 210, which they've done down here. See, it's 15 is 5 times 675, right, plus negative 16 times 210. Right. So let me show you on paper how I would do that. Right. So I'm starting here. Say I was again asked to find the greatest common divisor of 675 and 210. All right. So remember, the first thing I want to do is try to find what 675 mod 210. And over here, let's write out a little statement. These statements on the right are going to be very important for the second part, this extended Euclidean algorithm, where I write the greatest common divisor of two numbers as a linear combination of those two numbers. Right, 675 is equal to 210 times 3, right, for 630. I'll put this in parentheses actually. 210 times 3, that makes 630, and then plus 45, right? And then so 45, right? 45 is the remainder. And then again, by that greatest common GCD theorem earlier, the greatest common divisor of 675 and 210 would be equivalent to the greatest common divisor of 210 and 45. All right, so now I'm working with 210 and 45. So what is 210 mod 45? All right, so then off to the right here, I'll say 210 equals 45 times, and then 45 times 4 would be 180. Then I would have to add 30. Right? So 45 times 4 is 180, and then I add 30. There's my remainder, right? 30. And then another application here of the greatest common divisor theorem. So then this greatest common divisor I started with is equal to this, and this would be equal to the greatest common divisor of 45 and 30. So now I want to find what's 45 mod 30. And this is 15, right? 45 is simply 30 times 1. So I'm just going to put 30. I'll do it 30 times 1. All right, and then plus 15. And then one more application here of that greatest common divisor theorem. This greatest common divisor of 45 and 30 is equivalent then to the greatest common divisor of 30 and 15. Alright, but you see that 30 is a multiple of 15, so this is just 15. And 30 mod 15 is 0. So you stop, right? That means that this is meaningless, right? So the greatest common divisor is that last non-zero remainder, right, is 15. So 15 is the largest number. And so after all this, we see that the greatest common divisor of 675 and 210 is 15. All right. And you could also show this with prime factorizations, right? These numbers aren't that big, but as was mentioned in the beginning of the section, if the numbers were incredibly large, prime factorizations might not be the best way to go. It might be easier to do this. Alright, so 15 is the largest number that goes into both these evenly, 675 and 210. Now, what I wish to do, I want to write 15. I want to write 15, right, this greatest common divisor, as a linear combination of 675 and 210. Alright, so I want to have 15 be some number times 675, some integer, plus some integer times 210. And this is going to involve a lot of back substitution. So see all these statements I wrote here earlier with when I was trying to find the mods, when I was trying to find the remainders, all these statements. I'm going to use these, starting with the bottom one. And basically I'm going to solve for the remainders and do some substitution. So in the last statement, I'm going to solve for the 15. I'm going to get 15, because I want to have 15. All right, I want to have this. I want to have 15 equals some integer s times 675 plus some integer t times 210. So I want to have 15 alone in the beginning here. So in this last statement, I solve for 15. So 15 would be equal to just 45 minus 30. Because that's 30 times 1 is just 30, right? So 130. 45 minus a 30. All right. So that was the first remainder. Right? So I was solving for the first remainder right here. Right? Now the remainder before that is 30. I'm going to solve for 30 in that statement, right? This second statement, and then we're going to substitute it into this statement with 15 equals. So from this second line with 210, if you were to solve for 30, 30 would be equal to 210, then minus 4 times 45. And I'm going to leave it the way it is, with 45 times 4 like that. All right. Okay. And then we're going to substitute this for 30 in this equation where I have 15 equals. Right? I want at the end to have 15 be equal to some linear combination of 675 and 210. All right. So we have now 15 equals 45. 45 minus, and then 30, right, the remainder before that, solving it for in that line was 210, the quantity 210 minus 4 times 45. Well, distributing the negative here, we have the following. I have negative 210, negative 1 times 210, and then you have a positive 4 times 45 plus another 45. All right, there's a 45 here, and there'd be 4 45s there, so that'd be plus 5 times 45. 5 45s. Okay. So basically I'm kind of just going backwards where first I wrote 15 as a linear combination of 45 and 30, right? 45 minus 30. Now I'm writing 15 as a linear combination of 210 and 45. See, it's negative 1 times 210 plus 5 times 45. So I just need to do one more substitution to be able to get it as a linear combination of 675 and 210. Right? Just keep going backwards. So there, that was solving for the previous remainder 30 and substituting. Now I'm looking at this line. Go back here, these statements, I'm going to solve for 45 and substitute, right? So now I'm solving for 45 in this line involving 675 and 210. And we're getting from that line that 45 would be equal to 675 then minus 3 times 210. All right, minus 3 times 210. And then this statement, that's equivalent to 45, will replace the 45 in this last line here. All right. And that should be enough. Then I should have a 15 as a linear combination of 675 and 210. And let's see. So we have negative 210 plus 5 times, and then I'm replacing 45 now with this quantity 675 minus 3 times 210. And then we're going to distribute this 5 here, this positive 5. And now we have what we want. When I combine my two 10s together and 675s. So I've got 5 times 675. 5 times 675. And then you have 5 times negative 3 210s. That would be negative 15 210s. And you have another negative 1 of them over here. So negative 1 210s, negative 1 times 210, plus negative 15 times 210 would be negative 16 times 210. And here you go. This is what's being asked for. Can you express, the greatest common divisor of 675 and 210, which is 15, can you express that number as a linear combination of those two numbers? All right. And we can double check. I'll pull up a calculator here just to really hammer it home, double check our work. Is 5 times 675 minus 16 times 210, is that equal to 15? And indeed it is. So I've done it. I've expressed my greatest common divisor of two numbers as a linear combination of those two numbers. And as you've seen in this example, and I might do this one more time, it's just a lot of back substitution. Just take your final remainder, right, the GCD, solve for that, then solve for the previous remainder and substitute, then solve for the remainder before that and substitute, and you just keep going until you get to from the bottom statement to the top statement. And you should, and then of course combine like terms when necessary, and you should get this linear combination. All right, and they do that in this animation if you'd like to watch it. All right. So here so the image below shows a sequence of numbers generated by Euclid's algorithm on inputs 225 and 60, as well as partial results for the extended algorithm. All right. So here you just ask, 15, how is that a linear combination of 60 and 45? It's 60 minus 1 times 45, so the value of A is 1. Right? And then this 45 here, how could I get that involving 225 and 60? Well, I need, 225 minus 180, so B must be 3. Right? And then the two linear combinations above can be used to express the greatest common divisor of 225 and 60 as a linear combination of 225 and 60. How and how. So let me just do that again. Right? I'll show you again one more time here on paper. This is a little tricky, I find, for people the first time around. It's just a lot of substitution, though. So again, here I'm going to go through Euclid's algorithm and then extend it. Right? We're going to find the greatest common divisor of 225 and 60, and then write that greatest common divisor as a linear combination of 225 and 60. All right, so first, what's 225 mod 60? All right. So off to the side here, 225, that's equal to 60 times 3, right, 180, and then plus 45. So this is 45. Right. So then by that greatest common divisor theorem from the beginning of the section, this should be equivalent then to the greatest common divisor of 60 and 45. All right, now I'm finding what's 60 mod 45. Well, 60 would just be 45 times 1 plus 15, right? So that remainder is 15. And by that greatest common divisor theorem, again, this is equivalent now to the greatest common divisor of 45 and 15, which is 15. All right, now I know these couple examples, the greatest common divisor was 15. That's not always going to happen, right? The greatest common divisor of two numbers is not always 15. Please know this. It just so happens that these last two examples had that. And the reason I'm doing this right away is because 45 is just 15 times 3, right? 45 is a multiple of 15. All right, so this is going to be pretty quick. So I want to write 15 as a linear combination of 225 and 60. So first I'll take this bottom statement here. We'll solve for 15. Leaving things the way they are. 15 would be 60 minus 45. Right? And then I solve for 45 and substitute. Right? 45 from this line here is 225 minus 3 times 60. And then take this expression for 45 and put it in here with this 15 equals, right? We want to keep the 15 equals. So I have 60 minus and then 45 now is this quantity, this 225 minus 3 times 60. And I'm going to distribute the negative. Right? So finally we have 15 equals negative 225, right? So negative 1 times 225, and then, negative times negative 3 would be positive 3 times 60, but you also have one more 60 over here, so it'd be plus 4 times 60. So negative 1 times 225 plus 4 times 60. There's 15 written as a linear combination of 225 and 60. And this is pretty easy. 240 minus 225 would be 15. Right? That does work. So, what's the value in front of 225 here, right? Negative 1. And the value in front of 60, 4. Making those substitutions. I didn't check this one, but they're both good. All right. Now again, you're asked to basically just state those remainders, right? So like, what's 66 mod 27? Well, 27 times 2 is 54. Then plus 12, right, would be 66. And then you're doing what's 27 mod 12? Well, 12 times 2 is 24, plus 3 would be 27, so 3, and then see 12 mod 3 would be 0, right? And then the greatest common divisor of 66 and 27 would be 3. Right? Let's see what the next one looks like. Alright, so this is where you're solving for these remainders, right? How can you write 13 as a combination of 39 and 26? How can you write 26 as a combination of 65 and 39? And that's really all they're having you fill in there, and that should be pretty simple. Alright, and then finally here, they give everything to you basically. You just have to figure out what's the coefficient of 44, what's the coefficient of 36 in this linear combination of 44 and 36 that make 4. Alright, so pretty easy challenge activity, I feel. Alright. So now the final part of this section is on the multiplicative inverse mod n. And I think they're going to refresh your memory here. This was actually brought up before when you were introduced to modular arithmetic. But here it is again. A multiplicative inverse mod n, or just inverse mod n, of an integer x is some integer from 1 to n minus 1. Remember, when you're doing mod n, you're talking about the numbers from 0 to n minus 1. Well, 0 cannot be an inverse because you can't multiply anything by 0 and get 1. Alright, so it's one of these other ones, 1 to n minus 1, such that if you multiply x by s, if you multiply x by one of these, and then do mod n, you get a remainder of 1, mod n, you get 1. They give you some examples, right? 3 is an inverse of 7, mod 10. Because when you do 3 times 7, that's 21. But when you go mod 10, you got 1. Right? 7 is an inverse of 5, mod 17. Right? Because when you do 7 times 5, you get 35. Which, when you divide by 17, has a remainder of 1. Okay. It is possible for a number to be its own multiplicative inverse. Right? For example, 7 is the inverse of 7 mod 8, right? Because when you do 7 times 7, it's 49, but then mod 8, that would be 1. And be careful, not every number has an inverse mod n. For example, 4 does not have an inverse mod 6. Because if you do 4 times 1, that's 4. Which is just 4. 4 times 2 is 8, which is 2 mod 6. 4 times 3 is 12, which is 0 mod 6. 4 times 4 is 16, which is 4 mod 6. And 4 times 5 is 20, which is 2 mod 6. So, you multiply 4 by 1, 2, 3, 4, or 5, you're not getting something that's congruent to 1 mod 6. So some numbers don't have an inverse mod n. In fact, the condition that ensures that you'll have an inverse is if x and n are relatively prime. All right, x has an inverse mod n if and only if x and n are relatively prime. Remember what relatively prime means. That means that if x and n, if their greatest common divisor is 1. Right? 4 and 6 have a greatest common divisor of 2. So they are not relatively prime, so 4 would not have an inverse mod 6. All right. So some examples down here, what match each integer with its multiplicative inverse, mod 11. So 10 times 8 is 80, which mod 11 would be 3. So 10 and 8 are not inverses, mod 11. 10 times 9 is 90, which mod 11 would be 2, not 1. It's 10 and 10, right? 10 times 10 is 100, which mod 11 is 1, right? 99, a multiple of 11, plus 1. 7 times 8 is 56, which is 55, a multiple of 11, plus 1. So 7 and 8 are inverses, mod 11. And then 5 and 9, right? 5 times 45, 9 is 45, which is 44 plus 1, right? So 5 times 9 is congruent to 1 mod 11. Right? Pretty easy stuff. Now, we're going to use that extended version of Euclid's algorithm, to find a multiplicative inverse, mod whatever, of some integer. So they give you an example here. Suppose that you found the greatest common divisor of 31 and 43 is 1. They're relatively prime. So that means they should have inverses mod each other. So like for example, 31, the inverse of 31 mod 43 would be negative 18, but then that's not from 1 to 43, 1 to 42, so you'd add 43 and get 25. And that's what they're doing here. So 31 times 25, that would be congruent to 1 mod 43. And vice versa, you could also say that the inverse of 43 mod 31 would be 13. All right, so they give you some examples where they already write them out for you. All right. So again, I'm not going to go through this based on seeing my 2 previous examples. You should be able to do this after some practice, some exercises. But the greatest common divisor of 61 and 54 is 1. All right, they're relatively prime. So they should have inverses mod each other. All right. So if you were asked, what is the inverse of 54 mod 61? Well, if you look at how 1 can be written as a linear combination of 54 and 61, they're asking, what's the inverse of 54 mod 61? Well, look, 54 times 26. 26 would be the inverse of 54 mod 61, right? 26 times 54 would be 61 times 23 plus 1. So 26 times 54, when you divide it by 61, would have a remainder of 1. And 26 is between 1 and 60, right? If you're doing mod 61, so 26 for that one. And then same expression, now they're asking the other way around, what is the inverse of 61 mod 54? So see how 61 times negative 23 would be some multiple of 54 plus 1? Or it would be 54 times negative 26 plus 1. So 61 times negative 23 is congruent to 1 mod 54. So negative 23 is n inverse of 61, but negative 23 is not from 1 to 53. Right, we're doing mod 54. So just add 54. Right, add 54 to this. 54 plus negative 23 is 31. And you can check, and I'll pull up the calculator, but so 61 times 31 would be congruent to 1 mod 54. All right, I'll show you on the calculator. Right. If I take 61, right, take 61 times 31, that's 1,891. Now I'm going to divide this by 54 just to see what the quotient is. All right, we're doing mod 54. All right, so look at what 54 times 35 is. All right, 35. The quotient is 35. 54 times 35, you see, is 1890. See, you got 1 left over. So the inverse of 61 mod 54 is 31. Hopefully that made some sense. All right, and then you have additional exercises. Again, not all. I don't think all of them are assigned, but some of them are on your assignment. I would still recommend trying them all, though, just to get more exposure and more practice with the material. And you got the solutions you can look at too, but please, please, please try to work them out before you look at the solutions. Try to figure them out before, and then check the solutions, see how you did. Because if you're just copying down solutions and not trying, not practicing, you're not going to learn anything. All right. Now, of course, if you have any questions, send me a message and I'll get back to you as soon as I can. And thank you very much for watching.